Hello AP Bio, welcome to our video lecture on pedigree analysis. In this video, we are mainly going to be going through the pedigree handout that I am projecting right now. I gave this out the other day, or this is also posted to Classroom for you to print if you need to. Okay, so let's just get started. So first off, this first page just gives an example of a pedigree. So you can see in the key, squares represent males, circles represent females, a shaded shape means you have the disease or you have whatever trait we're tracking. Open circles or squares means that you do not. Here you can see we're tracking, in this case, we're tracking free or attached earlobes through 3 generations. So here I have the first couple. A horizontal line represents a marriage line. The vertical lines go down to children. So this couple had 1, 2, 3, 4 children. In this case, this woman married this man, had 2 kids, so these would be the grandchildren of the 2 grandparents. So I have this couple squared off here. So this, this trait tells you what the big F, little f's are. If a question doesn't tell you what's recessive and what's dominant, one fun little trick you can use is to find 2 individuals, find a couple that are the same, and look at their offspring. So here I have a man and a woman who are unaffected, and they have a child that is affected. The only way for that to happen would be for the trait to be recessive. 2 dominant parents can have a recessive kid, right? If this trait were a dominant trait, there's no way this kid got the dominant trait if it's dominant, which is not, from a parent that doesn't have it, okay? So if a couple has a dominant child, then one of the parents has to have it. In this case, this trait is recessive because 2 unaffected parents do have it. So as we go through these, if you're not sure what's dominant or what's recessive, if the problem doesn't tell you, look for 2 people that are the same, right? Particularly if it's recessive, and look at their offspring. Okay, so let's just get started. So here I have, let's read this together. Use the information provided below to answer the questions that follow. First, A, list the sex of the children in order of birth produced by the parents in generation 1. So here are the parents in generation 1. They have had 1, 2, 3, 4 kids. This would be a female first, then a male, then a female, then a male. So they had a girl, then a boy, then a girl, then a boy. Is the trait tracked in this pedigree dominant or recessive? How do you know? So let's look. So here I have, let's use my trick. Here I have 2 parents that are recessive. Well, I'm sorry, they're the same, but all the kids are the same, so that's not helpful. Here I have a man who doesn't have it, a woman who does, and I have both. Here I have a man that has it, a woman that doesn't. Here I have both. In this pedigree, you can't determine. You can't determine because there's, you could track it dominant or you could track it recessive, and both would work out. If I had to pick one, I'd probably pick dominant because it shows up in every generation. But based on what's here, you can't determine if it's recessive or dominant because you could track this pedigree as both. See, how many children did individuals 2 and 3 in generation 2 produce? They produced 3 children, right? So this couple had 3 children. What is the relationship of individual 6 in generation 2, so this individual, to the couple in generation 1? So how is she related to them? So that's their son, so this would be their daughter-in-law. Their daughter-in-law. Okay, cool. All right, let's do number 2. Albinism, lack of skin pigmentation, is caused by a recessive allele, so it tells me that it is recessive. Consider the following human pedigree for this trait. Solid symbols represent individuals who are albinos. So here I have a normal couple that have 1, 2, 3, 4 kids. 2 of them have albinism. What are the genotypes of the mother and father in generation 1? Well, they're normal, so they have, let's pick a letter. Let's use N for normal and lowercase n for albino. So they're both normal, so they're both big N. They have 2 kids with albinism, so they have to be carriers for albinism, right? In generation 2, what is the genotype of mate 1? So what is this individual? And then mate 2. So this individual is normal, so they're big N. My gut tells me they're big N, but they could be big N, little n. They might have, you would think that if they were big N, little n, you'd have at least 1 or 2 kids that were albinos. I guess the Punnett square would be 50%. So it's probably big N, but it's possible it's big N, little n. Mate 2, let's see, they are normal, so they're big N. They have a kid with albinism, so they have to be a carrier. In generation 3, what is the genotype of son number 4, so that individual? So they are normal because they don't have albinism, but one of their parents does, so they are big N, little n. And finally, can you predict the genotype of son 3? So this individual, can you predict it? So they're definitely big N something. So they're big N, or they could be big N, little n. There's no evidence that they're big N, little n because their children don't have it. Actually, they could be big N, little n because, both of these parents were big little. So you really can't say which one it is. Let's leave it at big N, or big N, little n. If they married someone that was big N, they wouldn't have any kids with albinism at all. So it's either one. Okay, moving along. Let's do a bigger one. The following pedigree traces a form of deafness in a family. This deafness is a recessive trait. That's good to know. Using the letters N for normal and little n for deafness, provide the genotypes for the individual indicated in the chart that follows. All right, individual 1-1. So this individual, we know they have to be normal because they don't have the trait. They have a kid that is deaf, so they must be big N, little n. And actually, we can label these, both these parents must be big N, little n, because they have a kid that has the trait. Individual 2, number 2. So they are, sorry, individual 2, number 2 here. There's a line missing. There should be a line right here. That's why I'm getting confused. Add a line right there. This part of the line doesn't just appear at random. Those are offspring. So they're big N because they are normal, but they have a kid with a disease, so they are heterozygous. All right, 2-6 is that individual. That individual, we know they're big N because they're normal, but there's no way of knowing if they're big N or big N, little n. So they could be either one. This individual right there obviously has the disease, so they are little n, little n. All right, 3, number 5 is that individual right there. So they are normal. Can I tell what their other allele is? Their kids don't give me much information. Neither does here. So they could be big N, or big N, little n. Let's see, 3, number 9 is that individual right there. So we know they have a big N because they are normal. Let's see. There's no way of knowing if they are big N, or big N, little n. So we'll put both. Line 4, number 4 is that individual right there. So they're normal, so they're big N. Can we tell the other allele? I can't tell, so it's big N, or big N, little n. And row 4, number 12 is that individual. This individual is big N because they're normal. They have a parent, though, that was a dwarf, so they are big N, little n. Okay? Okay. All right, let's move right along to the last page. The pedigree below traces brachydactyly, a condition in which fingers are abnormally short through several generations of a family. Those individuals affected with brachydactyly are shaded. Use this pedigree to answer the questions that follow. All right, question A. Let's move this up a little. Examine the children produced by individuals 6 and 7 in generation 2. How do you explain that number 9 is not brachydactyly? Okay, well, first off, is this trait dominant or is this trait recessive? The question doesn't tell me. And my little trick at the beginning of this video was to find 2 parents that are the same and look at their offspring. Here I have 2 parents that are the same in 6 and 7, and they have kids that are different. So this trait must be a dominant trait, because if this was recessive, all of their kids would have it, right? In a dominant trait, 2 dominant parents can have a recessive kid. 2 recessive kids can't have it, or 2 recessive parents can't have a dominant kid. So this trait must be dominant. So explain why number 9 is not brachydactyly. It's because the trait is dominant and individual number 9 is therefore heterozygous. I'm sorry, not heterozygous, is homozygous, forgive me, recessive. Okay, so let's pick a letter. So let's pick big B for the disease. I don't want to write brachydactyly, I'm gonna spell it, even though I know it's right there. Little b is normal. So that means these 2 parents are big B, little b, which means this individual is little b. Okay, so the trait is dominant, and number 9 is a homozygous recessive. Again, if this trait was recessive, 6, 7, and 9 would all have the disease, because 2 recessive parents, all their kids had to be recessive, have the disease. Is brachydactyly a dominant or recessive disorder? We just answered that question. It is a dominant disorder. Question C, what is the relationship between individuals 2 and 3 in generation 2? Ooh, these 2 individuals. What's going on there? We haven't said what that is. So obviously they have the same parents. The slanted lines, that means they are twins. You know, are they identical twins? Clearly not, because they have different genders, boy and a girl, and one has the condition and one does not have the condition. All right, let's do one more. Let's wrap this video up. Use the pedigree below to answer the following questions. Label the pedigree with Roman numerals and numbers to represent generations and individuals. Okay, I'm gonna do it over here. So this is generation 1. This is generation 2. This is generation 3. Generation 4. So we'll call this individual 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4. End it there. Who is most likely to inherit the disorder, males or females? So let's look at this. This one's a little bit different. So male, 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 female, male, 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 male. So males inherit the disease a lot more than females, which makes me think that this disease is sex-linked. Remember, autosomal means it's on chromosome 1 through 22. The normal chromosomes, the last pair being the sex-linked pair. How do you know? Mostly males have it. And if you're still not positive, the one female that has it right there look at her parents. She has a dad that has it. So individual 6 is a female. Individual 6 father has the disease, has it. Okay. So one of the X's that this individual got obviously came from the dad, and that X would have been diseased. When you see a pedigree, if it's way more men than women that have it, it's a giveaway. It's probably sex linked. Is this dominant or recessive? Oh, well, let's look. So my gut is telling me that it is recessive. So let's figure out, let's use our letters. It doesn't even tell me what the disorder is, does it? So let's just say that big N stands for normal and little n stands for the disease or whatever it is. Actually, wait a minute, I can use my trick right here. Here I have 2 parents that don't have it. I have a kid that does have it. That tells me that it is recessive. That's kind of a hint that it's recessive. So this male right here, all right, that's a male, so XY, and he has the disease, so we're gonna do that. All right, this female right here, she doesn't have the disease, she's XX. I'm sorry, this should be lowercase n, my bad. She's normal here, that would be a lowercase n. This individual would therefore have to be X, X, little n, little n. Okay, so my gut tells me this disease is recessive because my patterns here would have worked where this female here has a parent that has it, the dad has it, and the mom would be a carrier for it. Okay, I'm looking for any other clues on the pedigree. Yeah, my main clue is this one right here. If this were a dominant trait, one of these parents would have to have it because they passed on here. So it has to be a recessive trait. What is the genotype of the individual 3.3 marked with an asterisk? So that individual right there. So that is a girl, so it's XX. This girl is normal, so she has a big N. The other N, let's see, this is her dad. This individual is her dad, so that's an XY. The dad has the disease, so the dad had to give her a little n. Okay? All right, so I think that will be enough for this video. I hope that was helpful, and I will see you guys next time.